it's blinking.
Yeah,
It should be. I see. So it's already, it's on now. Fine. Thank you. Okay, so we'll be dealing with something which you partially already know, and what I will try to do is to shift accents, to shift emphasis, to change emphasis from those things that you are accustomed for practical purposes. For instance, all of you know what lattice vibrations are, how the phonons are introduced, how they are quantized, what is their spectrum, that there are acoustic phonons, there are optical phonons, and if you start thinking about all this, it may happen that something is eluding, so to speak. There is something fundamental in what I have said right now, just a second ago. And these are just general things, like symmetries, like broken symmetries, and like collective excitations known under the name of Goldstone knowledge. This will be our preoccupation. We will not be dealing with lots of details. Even though it's unavoidable, details will be everywhere, we will try to make emphasis on some general statements and general features. Because for some other purposes, you have some other lectures and other subjects when you can concentrate on some specific things. We'll try to maintain our discussion as general as possible. So what the course is about? The course is about, of course, about condensed matter, this is for sure. And what is condensed matter, there's no need to explain to you, because it's any condensed state which is characterized by huge density. The density is typically 10 to the power of 23 inverse cubic centimeters. And this is what the density is. This is what the density is in solids and crystals. The density of atoms constitute atoms. You can turn to metals, to electronic liquids, to metals or superconductors. The density of the carriers is nearly the same. You go to magnetic substances, the density of magnetic moments or spins, if you wish, is nearly the same. This is a typical concentration of atoms and constituent elements in the condensed stage. You may have several orders of magnitude lower. I mean, the density, if you start looking at the artificially created crystals, like those which emerge when you put neutral atoms on the surface of the specially designed lattice created by laser beams. And these are the so-called optical lattices, very fashionable these days, with lots of opportunities or lots of possibilities. You can actually mimic any model imaginable. You can get it realized and carry on experiments. It's very interesting. So several orders of magnitude lower doesn't mean that you have a great advantage. It's again huge number, 10 to 16, something like this. So the question is, when you're dealing with such huge number of degrees of freedom, how are you going to solve the problem? Are you able to take a cubic centimeter and put inside 10 to the 33 number of particles and then write down the same amount of the wave function for the same amount of variables? Can you imagine? If you write down the many-body wave function psi, depending on all the coordinates and the speeds and other degrees of freedom, and try to solve this many-body quadrant, you're lost. That's impossible. Right. So this is the most naive and expected judgment that for such huge numbers, straightforward tools and approaches don't work. So you have to invent something new. In fact, This technical obstacle is only superficial. It doesn't have a depth. It's an apparent difficulty, which everyone, even a kid, can see it. Many, too many, you can't work, right? But the problem is that when you move from a few particle physics to a many-body physics, with this concentration, something new happens. Qualitatively new, which cannot be extrapolated from your knowledge at the level of 2, 3, 10 particles. You have these aggregates of particles. Something new must be done to tackle the problem. This is the straightforward way doesn't get you to the desired point. Just to give you an example. I think it's quite a popular example, which being brought every time when people want to impress the audience. Take a biological system. Take a living organism, like a cell, a live cell. Under the microscope, you can see it can move, it can breathe, whatever. And you know all the chemistry of all the ingredients, the whole chemistry is known, suppose. You know all microscopic chemical reactions and constituents. Can you explain the life in this way? The answer is no, you can't. Simple, naive chemistry doesn't help you explain life, right? Another example. You take a metal with this concentration of electrons, and then you start lowering the temperature. And after some temperature, you see something amazing appears. Your sample loses its resistance. It transforms to a superconductor. A superconductor. A state which can sustain a constant current which is not decaying. It's a persistent current which can exist in a superconductor. For instance, in a superconducting ring, you can induce it, and once you did it, it's forever. Now, you know the Coulomb interaction between the electrons, you know electron-phonon interaction, you have interactions of the phonons with other degrees of freedom. Can you explain that below a certain temperature, you are going to undergo a phase transition from a normal state to a metallic, to a superconducting state? With Meissner effect, which is expulsion of all the magnetic flux from the interior of the superconductor, with Andreev reflection, with Josephson effect, what I'm just saying, telling you, it's all of them are Nobel Prizes, just to make sure that I'm not talking unimportant things. So the mere knowledge of physics on some elementary level cannot extrapolate this knowledge to the scale of a large superconductor with this amount of electrons, density of the electrons. So you need something new, something absolutely new and different from what you are accustomed to. So, in fact, the understanding of this qualitative change of physics and the way to describe this physics came to the minds of great physicists already in the first half of the 20th century. Perhaps I have to particularly mention the person whom we owe the whole name, the condensed matter physics. His name is Philip Warren Anderson. What he said, what his philosophy is in regard to what we are discussing now is the following. More is different. You add particles, first you don't see any qualitative changes. Quantitative changes, be my guest, of course they are. But after you exceed certain amounts, you see something new is happening, which cannot be extrapolated, cannot be inferred from what you've done from the, say, chemistry or physics of elementary particles on a microscopic scale. So his main statement is that physics consists, roughly speaking, of several levels of complexity. The lowest level is the level of elementary particles. Well, if I were a high-energy physicist, I would say it's not enough because I can go even deeper. I will go to the hadrons, to particles, whatever. No. Condensed matter physics for us, elementary particles mean electrons and nuclei. We want to move from one. I will explain to you, give you an example of these levels just in a second. We want to move from one level to another one. By accumulating knowledge at each level and promoting this knowledge to the second level, you reach nothing. Every time you have to establish new physics and new laws at each level. Here we have the laws, say, Newtonian mechanics or quantum mechanics at the very elementary level. Somewhere here we may have, or there, superconductors with Meissner effect, with expulsion of the flux, whatever. The laws governing this phenomenon and the motion of elementary particles are different. Just different. And they are, what is more important, they are the laws which exist here are as fundamental as those which exist here. In other words, if you are consistent in your judgments, in your logic, you can formulate the rules of the game, so to speak, of your background, just using this level and build upon it, without referring to what's going on here. Let me give you an example. It's a good example, quite useful to have in mind when you think in terms of different levels of complexity. It's quite an impressive example. So, imagine that you have a gas of low density gas, right? And then it's introduced a length scale R naught, which will play the role of a minimal length scale. Every time we'll be measuring distances, we will see that these distances are, of course, much larger than R naught. So, what kind of regime we have? Regimes we may have. We have an atomic gas of low density. Typical scale. The radius of a nucleus, 10 to minus 12 centimeters. The atomic distance, everyone knows. It's 1 angstrom, 10 to the minus 8. Now, if I go larger scales, I have a mean-free path, which is 10 to the minus 6 centimeters. This is roughly the distance the molecule or atom goes from collision to collision. Very roughly. Very roughly. And finally, you may have the wavelength of a sound, which turns out to be 10 such. So you have the whole hierarchy for length scale. This is the minimal one, then it increases, and reaches this one. And any of this scale can be chosen as your R naught. Once you identify the minimal distance with one of these numbers, you identify the level of complexity. Example. Suppose you chose your R naught to be 10 to minus 12 centimeters, which is the linear size of a nucleus. So therefore, we have to go to the next level, to the upper level, which is the level This one, the atomic level. Why I'm so confident in saying that? Because this level describes quantum mechanics of isolated atoms. When I solve the problem of an isolated atoms, I need to know all the characteristic features, the quantum numbers of the electron, and the ion which is inside, right? From ion, what do I need from ion? From ion, I need the magnetic moment and its charge. These characteristics, the nuclear charge or nuclear magnetic moment, are not part of quantum mechanics. It's high energy physics and it's theory of nuclear forces. It's much more complicated subject. So you cannot solve it using quantum mechanics, you need quantum theory. But that problem is supposed to be already solved. Once you solve them in the Schrödinger equation for a given atom, these parameters, the magnetic moment and the charge, will appear as parameters. We simply insert in those Schrödinger equations the parameters, known from somewhere else. So your level is this one, not this one. All right? Now, another example, we chose R naught being equal to L. The mean free path. What is the mean free path? You have to carry on investigation, watching the flows of molecules or atoms, but for that we need to know how the interaction and collisions occur. So that is the kinetic theory of gases, and kinetic theory of gases will determine for you the corresponding densities, the corresponding viscosities, whatever. All these things will not appear explicitly in the theory you're dealing with, because the theory you're dealing with will be hydrodynamics, in which all these parameters of the previous level appear as already being calculated by someone else and somewhere else, and in some other context. So this is exactly what I have in mind when I say different level of complexity, and it is absolutely impossible to jump from the atomic physics, which is determined by the choice of the minimal scale here, to the hydrodynamics, which is fixed by the minimal scale, which is this one. These two theories just have almost nothing to do with each other. What I'm saying is that every time you chose the level, be so kind, formulate all the principles and all the equations which are describing this or that regime. And every time you're dealing with a certain regime, the scale matters. Well, there are cases, at least one case, when the choice of the scale is not important. Have you ever heard about this at all? A system which is scale invariant, have you ever heard about it? I'm asking you. Do you know of any physical phenomenon in which scale is not a problem, is not an issue? All scales are equally important. Has anyone any idea about it? No, of course you have. You are simply detached from what you know because of my introduction. My introduction is a little bit. Okay. It's a critical phenomenon. If your system undergoes a second order phase transition, right? It's correlation length, which describes correlations between the densities or the spin densities separated by some distance. These correlations spread over longer and longer distances. At the critical point, all the distances play a role, equal role, which means that correlation length becomes infinite. In this case, if you have a small pattern of your system or make a magnification, you will get essentially the same picture. This is what is called scale invariance. There are certain cases, like all this philosophy. You see, I've spent so several minutes already to discuss this and describe this. Gets ruined immediately, because this hierarchy doesn't exist. There is only one. microscopic scale, which is the minimal distance, and all the others are much, much larger than this one and equally important. But it's a special case which we'll be dealing with perhaps somewhere in the middle, maybe by the end of our lectures. So all I wanted to say is actually what I have already said, that the mode is different, so we have to follow the logic that we cannot possibly start from the microscopic physics and derive large-scale physics and so on and so on. So what is crucial now for us, after all, the now large number of particles, it's unavoidable. Now, is it an obstacle or is it an advantage? If you start thinking about it, well, it would be an obstacle if you kept working with the old-fashioned single particle physics. You should not do that. You should do something better. But look, once the particle number is large, here we have to remember that in all those systems which we briefly mentioned, the particles are identical. If you have electrons in a metal, all electrons are identical quantities. Or you have a Boson liquid, for instance, like a liquid helium-4, then this is an interacting Boson system. So statistics becomes important. So first of all, statistics, even at the classical level, already tells you that the number of particles is large, then the relative error you make when measuring something or calculating something is small, because it goes like 1 over square root of number of particles. So this is a very, very small quantity. But on the other hand, this statistics has to be necessarily quantum. The quantum nature of the statistics shows up just because the particles are identical, and pure quantum mechanically, the ensembles of identical particles, if we believe, this is a kind of matter of belief, even though it's a reality, but it's still a matter of belief to a great extent. If you believe that the world is 4-dimensional, which means 3 dimensions go to space, 1 to time, then you have only 2 statistics. One is Fermi, and the other is Boson. Fermi, Dirac, and Bose-Einstein. And there is nothing else. It's a very clean mathematical proof that in 3 plus 1 dimensions, no other statistics is allowed. In 2 dimensions, it is much more subtle. There are exceptions. But here you have only Fermi or Bose. Now, when this Fermi or Bose statistics starts playing a role, you can derive it. If you know the main principle of quantum mechanics. In quantum mechanics, you have to associate a particle with a wave, as you remember, right? Quantum mechanics treats material objects, point-like particles, like let alone the sizes, point particles, as waves. And therefore, if I have the momentum of the particle, which is p, I can express it in terms of its wavelength using this very well-known formula. In fact, if you remember, the uncertainty principle operates with constants like this, right? Because the uncertainty principle, I would write down something like this. Of course, understood the square root of delta p squared and averaged over certain states, but roughly it's like this. Now, on the other hand, the kinetic energy of a particle with momentum p is p squared divided by m, which gives me h squared divided by m lambda squared. long. If you have a condensed system, the only distance which appears for so huge density is determined actually by the average distance between the particles. There is no other scale. If you have a density n, which is n divided by v, and which is 1 over a to the third power, then a is a relative distance between the particles. And of course, instead of this object, I can put this one. That will give me a square. And what is written here is, by the order of magnitude, the expression of quantum degeneracy temperature in ideal gases of the Fermi or positives. Either this or that. It follows without any calculations, by using common sense and using the basic principle. The quantum mechanics has an uncertainty relation, therefore there is according to the duality between the particle and the wave, I can write down this, and then the kinetic energy follows like this. And now I built up simply a thermal energy using the Boltzmann constant. This quantity has dimensionality of energy. In essence, is the same thing as the average kinetic energy. So this is the temperature below which quantum effects become important. So the temperature much greater than T naught is not sensitive with respect to whether you have a Fermi statistics or a Bose statistics, because at so high temperatures, you will have a Boltzmann statistics, which is no statistic at all. It's a statistical free particle, uncorrelated completely, right? So the new things will emerge in the opposite level. This is the one. Low temperatures. Now, is it something we are artificially trying to do to justify our lecture, for instance? No, sir, it's not like this. Because you ask if you have a Fermi gas, an ideal Fermi gas, or better to say, you have electrons in a metal, what is the kBT naught? The quantity of this type varies between 1 and 10 electron volts, which is order of magnitude or even greater than 10 to the 4th Kelvin. This is the temperature. 10,000 degrees. Maybe even higher. Now you go to the lab, to your fellow companion, who does not theoretical physics but experimental physics, and he holds in his hand a piece of metal, a plate, which he measures for the Hausmann alpha effect, whatever you want. What is the temperature? If he operates with the room temperature, so it's maybe a room temperature. Room temperature is 100 Kelvin. Two order of magnitudes difference. Okay. So already in this room, a piece of metal is a quantum object. Because electrons in this piece of metal are strongly degenerate. The distribution of these electrons in momentum space looks like this. This width of the order, this is this distribution, this is T, and this is, let me call it epsilon Fermi. This curve is inertial, basically a step, if you wish. The width is very, very small. It's a jump in the distribution of the electrons. So if you went to the very, very low temperatures, you will recall that in the ground state of a Fermi system, you have a monster huge ball of the given radius PF, which is determined by the density, such that everything inside is filled and everything outside is empty. So you see, we are so accustomed, so used to the fact that in case of Fermi statistics, we have this Fermi distribution. We don't even realize what is that. It's a ground state, ladies and gentlemen. It's nothing like, uniformly spread or dispersed in momentum space. Nothing like this. It's a very compact object. It is compact because there is a limiting principle behind it. It's a Pauli principle which does not allow you to put into each single particle state more than one particle. And this is why this ball blows up until all the particles are exhausted. And this is an object you have to live with. So you see, it's a very inhomogeneous object in momentum space, even though in real space everything's fine. Well, another example would be Bose-Einstein condensation. At low temperatures, all the particles tend to condense in a single state with zero momentum. It's another part of the same business, if you wish. Fermi statistics is replaced by Bose statistics, but the essence of quantum effects are still there. So, yes. So what to do in such situations? So in other words, the quantum effects as follows from this formula will show up much more vividly if we have light masses. Well, the electron is a light particle, and the densities are as high as possible. High densities is something which favors quantum effects in systems with high densities. The quantum effects become dominant. Now, so our idea is, given this parameter, which gives us the estimation of the quantum physics everywhere in temperature below this temperature, the degeneracy temperature, the quantum effects are important. And we see that it already happens for a metal already at the room temperature. The room temperature turns out to be a low temperature from the point of view of Fermi gas. So what to do then? What to expect? You lower the temperature. You lower the temperature. When you look at this formula, you see that when you lower the temperature, you increase the wavelength. Right? You increase the wavelength, which means that you start looking at longer and longer length scales. You start being interested in long distance physics. Low energy physics, long distance physics. Right? High energy physics, shorter distance physics. It's again uncertainty principle. You can rephrase one into another. So, at some moment, you start realizing that your effective distances, the temperature, are so low that the distances in which play a role turn out to be much, much greater than microscopic distances. And moreover, your physics no longer depends on the details of the interactions or couplings between different items like particles or particles and phonons, whatever. But it depends on something different. What is that? It starts being dependent on. And the features which have become very, very important when you go to the low energy limit, or long distance limit, but by the way, they both are known under the name of infrared limit. It's very often we use it. It's borrowed from high energy physics, infrared limit. This is typically distances much greater than microscopic distances, right? And the energies are well below than some characteristic energy. For instance, for a metal, when the Fermi statistics plays a role, this will be of the order of Fermi energy. So, what should be substituted instead? So when the microscopic details are unimportant, what becomes important? It becomes important what is called gross features. And these are only two of them. The first is, who has any idea what may be important when the micro details are unimportant? Can I speculate a little bit? Okay, here some knowledge of slightly different mathematics would be useful, but not only mathematics, it's also some common sense. What is important is space dimensionality. Because if you keep yourself within the realm of short distance interaction between the particles, the effective coupling between the particles will be determined how many directions do you have to realize these couplings. In case of one-dimensional lattice, each atom has two neighbors, to the left, to the right. On a square lattice, you have two more, because you add one more axis. You have d axis, you have 2d nearest neighbors. Right? So you see how the increasing the spatial dimensionality increases the effect of couplings and therefore the stability of your object. This is one thing. But the second thing, which is harder to appreciate, is the symmetry. It is crucially important whether you are dealing with continuous symmetries, one of the continuous symmetries, or with a discrete symmetry. A typical example would be, suppose I have a magnet such that my spins or magnetic moments may be aligned only along a different axis, along or opposite to it. So I allow myself to consider configurations like this, for instance. Right? But I cannot move your directions of your magnetic moments away from this axis. This means that's a limit, a very strong anisotropy. In real substances, there is something like this happens. These are called the so-called Ising spins. We'll have time to discuss them in some more detail. It turns out that this is not the only object. If I start measuring physical properties, I will come to a conclusion there is a phase transition there, below a certain temperature. Transition which will prefer the aligned orientations of all the spins. Either all of them up or all of them down. It's the same, because if the interaction between them is ferromagnetic, if there is a tendency towards mutual alignments of the spins, they may be aligned either along the axis or opposite. But this is the discrete degeneracy, which is called Z2. Right? Now, this is the spin system. Another model which is described in terms of the same phenomenon, in the same agreement would be, suppose I have a lattice which may be two-dimensional lattice, three-dimensional lattice, and then each atom in this lattice may be occupied either by the atom type A or type B. And there is a certain interaction such that if A is here, it prefers to have A here and not B. If B is here, then it prefers to have B's around and not A. So there is certain correlation. All of a sudden, it turns out that these two systems, the spin one and the alloy of AB components, are described by the same mathematics. And this mathematics is called the Ising model. Once you solve the Ising model, you solve millions of different physical models. What is behind them? Behind them is the notion of universality. This is one of the most important notions. This is what is called universality. As long as I keep the symmetry, in this case, this is the Z2 symmetry, which is, I have the spin up, I can overturn it down. And if I overturn it once again, I come to the original point. Which means that the symmetry group consists of two elements, identical and the reflection. If the symmetry is the same, and if the space I've chosen, because I can choose a one-dimensional sample, I can choose a two-dimensional sample, a film, I can consider a three-dimensional cubic lattice and put the spins there, or do the same with this. Once the dimensionality is fixed, the physics is going to be just the same. Irrespective of you are playing the games with the spins or with the atoms. In the vicinity of the phase transition. And there are many more examples of this kind, which I do not want to touch upon, because otherwise it will drive us very, very far away from everything. So this, again, it's a confirmation of the fact that there are gross features like space dimensionality and the symmetry, which play a crucial role. Among all those symmetries, one class of symmetries is absolutely important. And these are continuous symmetries. What is continuous symmetries? Well, the simplest, perhaps the most popular example is, okay, suppose you have a system of many spins or magnetic moments. All right, let me write it down, something like this. GR, R prime are the constants, and here I have an R. This is the classical vector, just let alone quantum mechanics, classical vector, another classical vector. So I have point R, and I point R prime, and there is some magnetic moment here, and another magnetic moment here. And this is the coupling constant, which depends on the distance. And suppose this coupling constant is positive, so this minus sign altogether it's negative. And for each pair, MR and MR prime, once J, the so-called exchange coupling constant, is negative with the minus sign in front, there is a tendency to form such a pair, to make them parallel. Scalar products should be made maximum, because the minus sign is in front. But the good question is, they must be parallel. But where should you look? Where should they look towards? What is the absolute direction for this polarization? So all the spins altogether will be polarized, staying mutually parallel. But in which direction? From this Hamiltonian, we see that if we rotate all the spins, all without an exception, uniformly, by a certain angle, around a certain axis, nothing is going to change because the scalar product is invariant under arbitrary rotations. That's the definition of the scalar product. So therefore, we cannot decide. So therefore, if we choose a sphere in the space of this magnetization and point the total magnetization solid here, and then turn it here, the energy is not going to change. because the energy only depends on the scalar property. And the scalar property in this case is just the same. Which means that we are dealing here with a huge degeneracy. The energy does not depend on the direction of the total magnetization. You rotate it arbitrarily, the end points touches an arbitrary point on the surface, and you can move it from one direction to another one without paying any energy, because the energy at each point is just the same. As a consequence, this rotation, the overall rotation of the magnetization, now you will listen carefully because this is very important. When you take all the speeds and you overturn them by the same angle, a little bit, to turn them by a certain small angle, but all of them in the same way, this would correspond to as if you had a wave propagating. At this point, the rotation is a little bit larger than this, then there is something like this. It's like a wave, and then you imagine and you send the wavelength to infinity. Then the whole system as a whole will rotate, because you will not change, you will not notice the change of orientation. It will be pushed over into infinity. In other words, if you have a rotation which represents a wave, in the limit when the wavelength goes to infinity, you have a rigid rotation. All of the spins do the same thing. Therefore, there should exist excitations with a frequency omega as a function of lambda. Instead of lambda, let me introduce k, the momentum, which is 2 pi divided by lambda, such that omega of k goes to 0 and k goes to 0, or when lambda goes to infinity. So in the limit of the uniform rotation, I don't have any potential barriers. It costs me nothing. You know what is that? This is the famous Goldstone Theory. You go to the second floor and talk to your fellow friends from high energy physics. This is something they start at the very first day. This is the bread and butter, Goldstone Theory. A typical example of a Goldstone particle, a Goldstone boson, is a standard acoustic phonon. This is precisely what the acoustic phonons are about. They are Goldstone particles. So there is no mystery, should not experience any complex on inferiority. Please. This is the same stuff as energy physics. This is condensed matter physics, but it also has the notion of the vacuum, of elementary excitations, particles, and the theorems. It's a different scale of events, but essentially it's the same physics. So this is a typical example. So, symmetries play a role. Symmetries play especially large role, big role, when the symmetries get spontaneously broken. Why I'm saying about broken symmetries? Because when I'm looking at this, this is the energy. But the energy is not, in statistical physics, the end of the story. Because in statistical physics, if we want to measure not the entropy, but the temperature, we have to apply to the free energy, right? Which is the energy minus T times the entropy. You remember how the differential of the free energy is written? So the volume and the temperature are independent thermodynamic variables. In other words, if you want to go back to statistical physics, you have to recall, if you want to use temperature as the independent variable again, it would be easier to handle the story in terms of energy alone, but it's not useful. We cannot, in the lab, cannot change the entropy independently. It's very hard. We don't know actually how to do it. We know how to measure temperature and how to change it, but not entropy, right? So therefore we use this one, and at this point we have the notion of disorder. At this point we have the notion of statistical weight and the entropy. So therefore there are two factors. The energy prefers alignment of the spins, and the entropy doesn't want it. So therefore at high temperature, when the tendency towards disorder is large, your system of magnetic moments is not ordered. It represents a random array of spins undergoing strong thermal fluctuations and not much correlated among themselves. But at low temperatures, you have something like long-range order, and in this case, their symmetry gets broken. Why? Because previously, as I said, you are able to rotate all this magnetization on the surface of the sphere. Once the nature itself chooses the direction along which the magnetization should look, this is fixed, and you can only rotate in the plane perpendicular to this one, so you lower the symmetry. If you rotate around z-axis, these are plane rotations in the plane. But you cannot change the orientation of the axis, because it is fixed already. This is what happens when the ferromagnet undergoes a transition from disordered to an ordered state. And it is just in that phase, in that ordered phase, where the Goldstone theory works. Only there, not in the paramagnetic phase. You have to have a long-range order and spontaneously rotate symmetry. So, the Goldstones, the phonons, the acoustic phonons, and crystals are typical examples. You know why we are so confident about the status of acoustic phonons? Because if you take a piece of lattice you remember what you do. Suppose, for simplicity, you have a one-dimensional lattice, and you write down, you numerate your lattice sides 1, 2, 3, and 4, n plus 1. And you write down something like this, and A0 when A0 is the lattice spacing, the distance between nearest neighbor sides. So n times A0 will be a fair representation for the ordered lattice. But after a while, when you start thinking about it, you will immediately ask the question, is this sample finite? Does it have the beginning and the end? Is the number of sides finite? This is one story. Then you ask, how do the endpoints look like? They're fixed, nailed by some device, or it is an infinite lattice, to the left and to the right. Or, for instance, this lattice represents a circle. In other words, I impose what we know all as periodic boundary conditions. I glue the endpoints, right? When the sample is infinite or it represents a circle, then some complications start developing, showing up. Why not to add here any number b? Who told me that it should be like this? Why not adding an arbitrary number b? Okay, if the lattice is infinite or represents a circle, then B, of course, should be located between 0 and A0. Because if B is greater than A0, I will add A0, make one shift, one rotation, and again reduce everything to the old stuff. But B may be arbitrary. In other words, here I have an external system when all the distance is already measured. And I identify the location of my atoms with respect to that reference system, say it's somewhere on the Pluto or Saturn or Venus, I don't know, Venus. So therefore, I allow myself to consider any shift, any B, and nothing is going to change. In other words, I will take my lattice and move it as a whole by a distance which is smaller than the distance between the nearest neighbors. What happens? Nothing. Because the energy is collected from interaction between the electrons, and not from their location with respect to something else. There is no force which is imposed on my lattice from outside. All forces are internal. And this is a self-consistent solution, actually. I minimize the potential energy in such a way that the lattice is stable. The problem of stability is a separate problem, but it tells me that you are entitled to make a shift, uniform shift of the whole system without any price to pay. This is precisely the same as what we were doing when we were rotating the magnetization on the surface of the sphere in the previous example. So we conclude, therefore, once we have a certain realization for some particular B, we have a broken translational symmetry. Translational symmetry is broken. Every time you have a lattice, translational symmetry of empty space, space in which you have nothing. You remember how the conservation of momentum was derived. The space is empty, all distances, all translations are equivalent. You can move the particle from this point to that point, nothing is going to happen. Now, no forces which a particle experiences, the momentum is conserved. Right? Now, you have broken this, because instead of that, you have these periodic arrangements of your atom, and you fix them. But you could have fixed it a little bit by shifting, or again shifting, and you have a continuum within this interval. It's a continuous transformation that you undergo, a translation by one lattice spacing. It's a slow process, which has the beginning and in the end. In the beginning and in the end, you cannot distinguish between the two states. They are identical. In fact, they're identical at each intermediate stage, which means that you again have strongly degenerate ground state or the minimal energy state. As a consequence, the Goldstone theory works, and they should exist quasi-particles which recover the broken symmetry. What are those particles? Acoustic photons. So you see, it is not as simple as it might seem. Well, you go in the standard course of solid-state physics, you learn about acoustic photons. You don't care about the Goldstone theory. You have a system, you derive equations, the quadratic equation, the quadratic form, you derive it, you minimize the energy, you find the solution, you can look at the vibrations, and then you derive from some very general principles. And there is one point, though. You may ask yourself why omega of k should go to 0, and then you accurately look into content of that statement. If you are careful, very attentive, you will find out it's about translational invariance. So this is a kind of, this was a kind of, advertisement, if you wish. Our everyday work will not be like this, because I don't like too much discussing on topics without putting real materials on the blackboard. This is unfair. We should learn something, but we should be able also to generalize, to understand what we are doing. A few remarks about how our work will be arranged. You have to know it because, well, it's a long-lasting tradition that students solve problems. I'm sure that in other subjects you do just the same. I'm absolutely convinced that the problems play an important role. In my case, it will be maybe even more important. First of all, you will have the lecture notes, my lecture notes, which are at Signora Sandra and Patricia, so they can distribute. I have to ask her to do that maybe in a week or something like this. You will find problems there, you will find references there. So don't ask me which books to read or to look at, whatever they will be. Something. On top of that, I will distribute some extra materials. So the problems will come on a regular basis, whether we want it or not, but without it, it doesn't make sense. Not because it's hard to estimate your advance and your progress, even though this is also the case, but the main task with the problem, with solving problems is not this. It's to make your knowledge active, operative. I would like to see you able to solve problems, to pose the problems, and to analyze and to judge. This is very important. Okay, so this was kind of very vague introduction. Just to summarize, when you have large complexes or aggregates or particles, you have to change gear, change your approach, replace it by something different, and pay attention to something which is to those features of the system, especially at low temperatures and long distances, which capture the main properties. And these are, of course, as I said, dimensionality and the symmetry group. So the effective theories will look like continuum theories when short distances don't play much role. Even though you will be, in certain cases, will be able to cover all the distances of the problem, even though this is not terribly interesting. The most interesting part has to do with infrared limit, long distance. And then we'll find out many curious and amazing features and things happening with this effective description. I hope you'll appreciate the beauty of this approach, because if you drop into a library, or simply if you ask me what to recommend, you will find out there is an increasing number of textbooks on condensed matter physics with a strong emphasis of quantum field theory aspects. Sometimes the textbooks is called the field theory of condensed matter, which immediately tells you that we are just there. We are the members of the club. The people who write the book, these books are excellent high-energy physicists, in fact. So this is, of course, I'm not saying that those gentlemen, ladies and gentlemen working in that field don't have their own problems. There are lots of them, many interesting, intriguing, breathtaking problems. Nobel Prizes come one after another. But look, condensed matter physicists also did very well. A couple of years ago, there have been a few very impressive advances in the field of topological quantum field theory. And those people were here because they received the Dirac prizes. And some of them then after that became Nobel Prize winners. So let us turn to something which is very, very simple. By the way, is this the only device which is here? Because I think it's not doesn't clean as much as he leaves the white trace, right? For instance, if I erase this, nothing else. Okay. Let us start more accurately looking at the problem of vibrating lattice. For simplicity, just only for simplicity and not for some other purpose, we will describe lattice vibrations in the one-dimensional case. So therefore, we will consider n particles with the Hamiltonian. This is the kinetic energy. And this is the potential of the atoms, which are coupled by some elastic forces, and these elastic forces are described in terms of some potential, which depends parametrically on the coordinates x1, x2, and so on. What is assumed? What is assumed is that if I minimize the potential energy, its solution will look like Xn and A naught, and let me write down this B for the already explained reason. So there is certain distance between the atoms. At equilibrium, the atoms arrange themselves in the lattice such that the location of the atom is parameterized by this formula. N is the number of the site, A naught is the interatomic distance, and B is an arbitrary parameter, a length, which is located within the interval. If I choose exactly A naught, this will be the same as if N is replaced by N plus 1. This is why this restriction. Good. Well, because of this B, we understand that the ground state is degenerate, is infinitely degenerate. Any B which belongs to this interval spontaneously breaks translational invariance. This is a highly non-trivial statement. If I make a shift xn is goes to xn plus y. Y is not necessarily limited by this interval, an arbitrary number. Right? Of course, the kinetic energy is invariant because this is a coordinate and this is the momentum. But here, if I make such a shift, x1 plus y, x2 plus y, and so forth. It's just the same as it was in the beginning. This is what is assumed by full translation invariance. Of what? Of the ground state? No way. Of the Hamiltonian. This is very important to understand the difference. Of the energy. If you shift the whole lattice by any distance, any whatever you fancy, the energy is going to be the same. This is what is called translation invariance. Full translation invariance of full empty space. Then you minimize your energy. And immediately realize that something went not in the right direction. Translation invariance gets broken. Because what you obtain is this one. This multitude does not describe free space or operations in free space. All you can do, you can make a jump from n to n plus 1 to n plus 2 to n plus 3. It's a discrete symmetry. It's no longer a continuous symmetry at all. Right? So this should be remembered. Well, I have to add here, as a result, we have to have a Goldstone modes. And this turns out to be nothing but the acoustic formulas. We have to show all what I'm saying, we have to show it. If number 1 is already present because it's written here, all the rest needs to, yeah. These Goldstone modes, the content of the state monad should be some constant, which is called sound velocity times the modulus of k, when k a naught is much less than 1, which means when the wavelength of your excitations is much greater than the latest space. What is called the long wavelength limit or infrared limit. And in this limit you have this linear dispersion. This is precisely the dispersion of the Goldstone modes. Well, now here comes the crucial step. What should we do now? We wish to calculate the spectrum of this system. And the first thing we will do, okay, let me say it again. What I'm discussing here is something that you already know. You know the latest vibrations, for sure. What I'm trying to do is to put new emphasis on whatever is going on. So nevertheless, we will need to solve the equations. So what we do, we can, for a moment, it's actually up to you, but let us choose b equal to 0. We can keep all the calculations with no 0b, but it's simpler to do. Now, for a vibrating lattice, what happens is that each atom undergoes a shift, a small shift from the equilibrium position. Right? So therefore, I can write down that as a function of time, x and t is NA naught, this is the unperturbed value, it's the latest value, and plus some displacement un, which is time dependent. There is a catch here. It's very easy to make a mistake here. Because if you skip one point, then it will ruin all your calculations, even though this is elementary for you. This expression only makes sense if the absolute value of un is much less than a. Is it clear? Why the displacement has to be small? Because so far I didn't impose any other restrictions, right? Because how do you know that u and t is the displacement of the nth atom? How do you know that? For instance, if I started from here and brought this particle, this atom somewhere here, 5, 7 lattice spacing away, that means that my lattice starting melting. It's no longer a lattice in the zero order approximation. In other words, I cannot go far away from the ground state, from the equilibrium state. I can only consider small fluctuations. Therefore, whatever happens with this quantity, if it's supplied with index n, it should be much smaller. Its deviation from the given atom should be small. In other words, the displacement must be very, very small. If the displacement is small, then I can plug in this expression into this and expand this u, which will coincide with its equilibrium value when all of u's, small u's, are 0. And then I will have a term, a second order term, and then I also have the higher order terms. This is an expansion, a Taylor-like expansion in small quantities, u and m, small displacement, but I do not have the linear term. Is it clear why I don't have a linear term? Why linear terms are not present? This you should know. Who can tell me? You can? Can you?
It's like it's in the equilibrium position, so the first derivative should be 0.
Absolutely, yeah, of course. That's the equilibrium position. It's an equilibrium condition. The equilibrium condition is the force acting on the end atom should be defined as minus du at un equal to 0. Once you apply this, you immediately arrive to the conclusion, that there is no linear terms. So it's a quadratic form. And this is what is called the dynamical matrix. This matrix which determines everything. Once you know it, you know everything. Of course, you drop what is called the anharmonic terms. The higher order terms describe what is called anharmonicity. Because roughly speaking, what we have in mind when we consider lattice vibrations is the problem of oscillator. The oscillator is characterized by a parabolic potential well, but if the parabolicity is not enough, sometimes people add higher order terms, but we don't do that because we are staying within the harmonic approximation. That's important. What we do here, we are staying within the harmonic approximation. I will make a few steps forwards and then we'll stop until next time. Now, a few properties of this dynamical matrix are obvious. Look, un are real numbers, real functions of the arguments, and therefore automatically and necessarily this matrix has to be symmetric. Because if it is not symmetric, only symmetric part will survive. If I interchange un and un, simply change the labeling, the expression should remain the same. So therefore this follows it. The second problem is, in fact, this dependence has this structure. It doesn't depend whether you go to the right or to the left. The distance matters, and therefore this is here. So the first two properties are self-evident. You don't need too much. You don't need to think too much to arrive at this. But there is one more thing, which is much deeper. It has to do again with the symmetry. Which symmetry? Translation symmetry. Again. If I take my sample, whatever is the configuration, if I take it as a whole and make a shift by any distance, nothing is going to change. We have already discussed it. It's up to me to start measuring the distances from this point or from that point. So therefore, if I translate it by any distance, as a whole, of course, you have to add under the condition that the lattice is infinite. Or you impose periodic boundary conditions. By periodic boundary conditions, I would say that it would be, should look like this. Or n goes to infinity. It's better to have it like this. So if I choose u of n being equal to epsilon, the same number for any n, which means that the shift of all the atoms is just the same. Nothing is going to change and to happen. Which means that if I plug this into here, the change of u, which is sum of 1/2 n a n m epsilon squared, should be equal to 0. Right? But now please take into account first. Epsilon is non-zero, therefore all the rest must be 0. But all the rest is a double sum. And this quantity depends only on the difference. So therefore, the true condition which I have here is L goes all L, all L, from minus infinity to plus infinity. A L is equal to 0. That's the condition imposed by the translation. So this matrix cannot be arbitrary. It's subject to this condition. As a result, omega of k will go to 0 and k goes to 0. But that I will show you next time. So again, all the way of this derivation, we'll be talking not about the atoms which go, some of them to the right and some of them to the left. We'll be talking about very general things, basically and dominantly symmetry, and the patterns of the spontaneous breakdown of those symmetries. So it will be kind of field theoretical course which I'm going to give you. Not exactly, but to the great extent. Questions? Today it's hard to ask questions. I understand that the lecture was quite general. But nevertheless, maybe you have any ideas or questions. No questions. All right, so now I have to stop this device by pushing this.